In this video, we're going to be talking about discontinuity, when the function is not being continuous. Dis meaning not, so no continuity. There are three major types of discontinuity that we are going to be talking about. The first, removable discontinuity, we have a good limit, however, the function is not equaling that particular value. We could have a value, but it's not equaling the limit. Infinite discontinuity is when the limits are heading towards infinity. So they could both go towards positive infinity or both negative or kind of split like this. We get an infinite discontinuity. It's similar to asymptotes. Jump discontinuity is where we do not have a limit. So no limit right here. It's not heading towards infinity, just straight, no limit. Then you have a jump discontinuity. So in this example, we have the function heading towards particular value, in this case c, and we want to see what's going on. So as we come in from the right, we are heading towards -3. And as we come in from the left on that red arrow, we are heading towards +3. And you say to yourself, oh no, those two things are not equal to each other. Since those things are not equal to each other, the limit does not exist. And neither of them are heading towards infinity, meaning that this is a jump discontinuity. If you do not have a limit, then you have a jump discontinuity if neither limit are heading towards infinity. In this example, we want to see what's going on as we head towards -1 and check it for continuity. As we come in from the right, we can see as x is approaching -1 from the right, we are heading towards 0. As we come in from the left, this function is approaching -1. It is heading towards 2. Dang it, those two things are not equal to each other. 0 and 2 are not the same thing. So here our limit does not exist. If our limit does not exist and neither limit is heading towards infinity, we have a jump discontinuity. We can see that jump discontinuity very easily on the graph because the function jumps from being one thing to being something else. In this example, we want to see what's going on as c is heading towards -3. As we come in from the right, we are heading towards 3. Okay. As we come in from the left, as we are approaching -3, we are also heading towards 3. Oh, cool. Those two things are equal. So the limit of this function is 3. However, the value of the function at that point, f of -3 equals 4. Hey, that does not equal 3. So what the function is actually spitting out at that value, -3, is not equal to what the limit is. That makes it a removable discontinuity. Depending upon where you're working, sometimes removable is also called a point discontinuity, but removable and point discontinuities are the same thing. In this example, we want to see what's going on with c as approaching 3. We start as we come in from the right. As we head in this direction, we can see that the function is heading towards 0. As we come in from the left, we can see once again, hey, that function is heading towards 0. Since those two things are equal, cool, we got a good limit. Our limit is 0. But then we want to check, is our limit matching up with what our function is doing there? Well, so what is f of 3? Well, it's not here, it's up here. It's at 1. So f of 3 equals 1. The value of our function is not equal to the value of our limit. So this function has a removable discontinuity at x equals 3. Removable discontinuities mean the same thing as a point discontinuity, depending upon what you might see, like textbook differences. Yeah. If we looked at the rest of this function, based on what we can see in this window, this is the only point where we have that removable discontinuity. Everywhere else where the function is heading is equal to what the function is spitting out. It is just at this value of 3 where we have that discontinuity. In this example, I am trying to figure out what are my points of discontinuity. So graphically, it's pretty obvious. We have an infinite discontinuity because this function is heading towards positive and negative infinity. But what if I wanted to figure that out algebraically? Well, I would just start by checking my limits. So I know I'm going to be in trouble if this denominator ever equals 0. So when x minus 1 and x minus 3 equals 0. Neither of these two factors are going to cancel with my numerator. So they are causing some discontinuities there. If they had been able to cancel, they would have been removable discontinuities because I could have written the function without those things in the denominator. Anything that cancels is a removable discontinuity. Things that can't cancel with the numerator create infinite discontinuities. So these are both infinite discontinuities because they do not cancel with our numerator. That is it for our video on discontinuity. A reminder that continuity needs to make sure that the limit of the function equals what the function is actually doing. There are three major types again. The first being removable discontinuities, where we have a good limit, but the function is not equaling that value. This could be that it is 0 in the denominator that we could cancel out. An infinite discontinuity is when our limit is heading towards infinity. They could both be positive, they could be both negative, or swapped. That creates infinite discontinuities. And finally, jump discontinuities is when we are not able to get a limit value from our function. So then we have a jump discontinuity, but neither of them are infinite. Thanks for watching. Bye bye.